Hello there, everybody. Welcome to another Chem Complete episode, and I am Professor Tomney. We are going to be continuing our lecture on carboxylic acids today, and in particular, we're going to take a look at some of the properties that carboxylic acids have, including what makes carboxylic acids acidic in the first place, what additional factors might influence the acidity of carboxylic acids, and then we'll also take a look at the intermolecular forces in play and how that affects the boiling point of carboxylic acids. So that is coming up on the channel right now. Okay, thank you so much for using Chem Complete for your learning resource today, and let's go ahead and get started. So what makes carboxylic acids acidic as a functional group? Well, in order to address that, let's take a look at a carboxylic acid. So we'll use acetic acid to keep the example simple. An acetic acid would have the carbonyl group, it would have the hydroxyl group on the other side, and then it would have that CH3 group. Okay. So, if we take a look at this, the reason that this compound is so acidic really has to do with its conjugate base, right? So if I turn around and I use some generic base that we'll just call B, that base would come and grab this proton, and these electrons that would be shared between the bond of the oxygen and the hydrogen would be deposited onto the oxygen. So what I get through this deprotonation process is a conjugate base, it's an anion. And the main reason that that hydrogen is acidic is that this conjugate base is resonance stabilized. Okay, so the real answer to this in a single word is resonance. A lot of my students always like to joke around because I'll ask a question and they usually know that 90% of the time the answer is either resonance, hyperconjugation, or sterics. And it does explain a lot, those three concepts, okay? So resonance is the main driving factor for the acidity here. And if we were to take a look, one of these lone pairs could form a pi bond here, and then we could push one of the pi bonds up to create a new set of lone pairs, right? And then we would have an alternate resonance form that would be equal in its contribution, because in both of these cases it's a oxygen that is handling the negative charge, right? And then we would have this. So, resonance is the main driving factor between carboxylic acidity. Now, what additional factors can influence the acidity when we start taking a look at carboxylic acids? Okay, so the main answer here is it's going to depend on the substituents that are going to be around or in near proximity to the carboxylic acid. And more specifically, we are going to be taking a look at these substituents and determining, is it an electron donating group that is nearby, or is it an electron withdrawing group that is nearby, right? So electronegativity is going to be in effect here, and donating through resonance might be in effect here, so we have to consider those factors. Okay, so to give you a first example where we can take a look at this at play, go back to the acetic acid that I had before. So in this case, I'm actually going to draw the hydrogens out here, all three hydrogens for the CH3 group. Okay, and then I've got my C double bond O, and I've got my OH. Okay, versus, let's do the same thing, but this time we're going to put fluorines instead of hydrogens in proximity to the carboxylic acid functional group. Okay, so the big difference here is that fluorine is the most electronegative element. It has high potent withdrawing effects on anything that it is surrounding. So the question becomes, well, is this going to make it more acidic or less acidic? Well, if I take a look at what's left behind, right, let's just call it R for the general purpose of explaining this. If I have a carboxylic acid and it has been deprotonated, I have a negative charge because I have an excess buildup of electron property, and electrons are negatively charged. So what that means is that if I have something like the fluorine that is going to be an electron withdrawing group, it's going to have the power to take some of this electron property and divert it or pull it towards itself. And that's a good thing as far as stability is concerned. So this conjugate base is more likely to form because it is a more stable conjugate base. And because of that, we would expect that the fluorine-based acid is more acidic. Well, why is it more acidic? It's more acidic because it is a higher probability that the conjugate base could form. The conjugate base is more stable, so this compound is more willing to let go of that acidic hydrogen in comparison to the acetic acid over here, which doesn't get those same effects. And indeed, we can see that on display here, because if you take a look at the pKa value, the pKa for acetic acid is 4.76, while the pKa for the trifluoroacetic acid is going to be a pKa that is negative 0.23. So several magnitudes more impressive as far as acid strength is concerned there. Okay, now that's just one example. Another example that you can take a look at, and usually by the time you're talking about carboxylic acids in class, you've gone through aromatics, but this may not make quite as much sense if you haven't had aromatic lessons yet. Okay, so if we take a look at the aromatic system, we could take a look at benzoic acid, which is just the carboxylic acid with the hydroxyl group present there. Okay, and then let's take a look at two other different types of derivatives. So let's take a look at a benzoic acid that has an electron donating group, and the electron donating group that we'll use here will be a methoxy group. And we go ahead and we put our carboxylic acid right here. Okay, and we can also do another one, but instead of a donating group, this time we'll do a withdrawing group. So one of the best known withdrawing groups is the nitro group that we can put on the ring there. Don't want to forget that this is aromatic. And then there's the benzoic acid part. Okay, so these right here are the acidic protons that we're talking about. Because this oxygen with lone pairs is going to donate into the ring system, this electron donating group is going to cause the acidity in this case to go down or to become less acidic, okay? Because what's happening is the conjugate base, just like we showed up here, when that conjugate base gets its negative charge, it does not want a group donating additional electrons towards it as it's already handling a surplus of electrons. So that's actually going to damage some of the acidity property, whereas the withdrawing group, right? Here I've got the electron withdrawing group. That is going to enhance the acidity, make it stronger or more acidic, and that's exactly what we see, okay? So the pKa values that I get across the board here, regular benzoic acid is 4.19. The methoxy donating group, I would expect it to be higher in pKa because it's a weaker acid, and it is indeed. It is 4.46. And then the electron withdrawing group with the nitro, I would expect that to be lower than the benzoic acid. And it is because that nitro has the ability to help stabilize that conjugate base. And so it's got a pKa that is going to be equal to 3.41. So we can see that that one is more acidic than the others in regards to that. Okay, so the last thing that I want to take a look at here in this lecture before we wrap up is why are carboxylic acid boiling points so high? And a lot of it has to do with their geometry and the strong intermolecular forces that are at play here. Okay, so in particular, because of the OH group, we're going to have hydrogen bonding occurring here, similar to what you would find in water, alcohols, other organic solvents that contain OH or NH groups. And so carboxylic acids have the hydrogen bonding capability, but their structure also allows them to have two hydrogen bonds between the two structures, and they end up creating very strong dimers, okay, which is a unit of two of the same molecule. So I'm going to try to help illustrate this here. Here is the first acetic acid, okay, and then the second acetic acid, we're going to draw it this way in solution because it would kind of have free rotation around in solution as we're working with it here, okay. And then here's the CH3. So if I were to take a look at this oxygen being partially negative and this hydrogen being partially positive, I can form a hydrogen bonding situation between those two, and I can do the same thing right here, right? Partial negative, partial positive, and these coordinate together. So this hydrogen bonding activity or linkage set that you get here is responsible for why the boiling points for most carboxylic acids are going to be pretty high. Usually they're going to be above water most of the time. So the reason for that, again, is the intermolecular forces. The heat, the thermal energy has to break apart these forces in order to start the transition between phases. So if you've got a liquid and you're trying to heat it up to go to a gas, it's all that extra energy that has to be put in to break apart these hydrogen bonding effects between the dimers there. Okay, so that is it. That covers the major properties and effects of carboxylic acids. So if you haven't already, hit the subscribe button so you can stay up to date with your studies as we're releasing new content. If you would like to support the channel, you can either use the thanks button or head on over to our website at chemcomplete.com. There's lots of affordable options, guides, walkthroughs for difficult subjects over there for only a couple of dollars. So thank you so much for choosing ChemComplete as your learning resource today, and I will see everybody in the next video.